All right. As you can see, we're going to be reviewing the uniform circular motion concepts. And then what I would recommend you be doing as we start the new unit on Thursday is to go ahead and begin watching daily videos from the AP Classroom site on Unit 7. So today we're not covering anything new. In fact, the whole last week before the winter break, we didn't cover anything new. We were just practicing different kinds of problems. Same thing today. We're just going to give you a chance to review, kind of refresh your memory on what uniform circular motion problems look like. I give you a chance to solve several different kinds, both individually and in groups. And then Thursday, we'll be starting rotational motion. So remember, uniform circular motion is when something travels in a circle, but rotational is when something actually spins around its own axis. So the Earth would be a good example of something that exhibits both. So the Earth travels in circular motion as it orbits the sun, but it also travels or has rotational motion as it spins around its own axis. So we're focusing today still on uniform circular motion, and then starting Thursday, switching gears slightly to rotational. And then these next 2 weeks after this week, we'll continue studying rotational motion. And then that'll leave us about 3 weeks before spring break to learn energy, work, power, and momentum. And they all kind of go hand in hand. It's a little weird to me that College Board separates that into those topics into so many different units, because to me, they all kind of go together. You don't generally teach them independently. So they've separated them for some reason, but I include them into one unit on my material. So some of the things where they've put everything into one unit, I break it into sections, and this one is one where it's just the opposite. I see it kind of as all as one big topic, and they divide it out. So but we had been going through Unit 3 on the AP Classroom site, and now we're jumping ahead Thursday to Unit 7. So to help prepare you for that, I would advise you to start watching those daily videos from Unit 7. And then you do have 3 assessments that are assigned to you, and they're listed here on the screen. And they will be due, the first one due next Monday night. So you have 1 week to work on that. You won't need a week to get it done, but I'm trying to give you quite a bit of lead-in time. Hopefully you'll get that done in the next few days, and you can just go ahead and start working on Unit 15, which will be due the week after, and then Unit 16. And actually, Units 15 and 16 are due close together. One's due on a Tuesday and one's due on a Thursday, basically 2 weeks from now. So you have quite a bit of time in the big picture. And Unit 16 is the smallest of the 3. But Unit 10 is what we've been studying prior to the break, and then what we're kind of reviewing today, and that is uniform circular motion. And then Unit 15 is on torque. And so I wanted to push that down the road a little bit, because we won't even start learning about rotational motion until Thursday this week. And then next week on Monday, we're going to start talking a little bit about torque, but I wanted to make sure we had a couple of lessons on that before you had to start doing that assessment. So that's not due for a little ways down. And then Unit 16 is on the final concepts of rotational motion, things like angular momentum, which will be probably covered towards the end of next week. So that's where those assessments line up. And you should complete those on your own pace, just by the due date. So again, I'll show you on the calendar here in a minute, but Unit 10 is first, and then 15 and 16. They are quiz grades because they are assessments, and so you'll all have different questions with different numbers, different order, but you'll have the same number of questions and from the same units. And so this is assessment tab. When you open up Positive Physics, make sure you're doing the assessment tab. And because it's the assessment, remember the format is that you answer all the questions, and then when you're finished, you click finalize, and then it allows you to go back in and do corrections. And your grade will be, like we've done before, the average between your corrected percent and your original percent. So you obviously want to do the best you can on the first time through, and maybe use the work section to practice and watch the videos and such. But the grade will be an average between the original and the corrected. And you, like I said, it's on your own pace to some degree. You just have to get it done by the deadline. So we're not going to do it when you see it on the calendar. That doesn't mean we're doing it in class that day. You have from now until then to get it done. So it's much more self-paced. And since I feel comfortable doing that, because quizzes are only 10% of your grade, in terms of the weight that it bears on your grade, it's the same as homework. So I'm treating a little bit more like homework in that regard, giving you more time to do it and letting you self-pace. And I think we'll continue to do that through this unit just because we're still on this transition where this week we're still mostly remote with only a few students in class. Next week, we'll probably see those numbers start to shift a little bit, but I think it's going to be a few weeks before we have more students on campus. That's my assumption based on some of the things I'm hearing and reading in my emails. So I think for now, for this unit at least, we're going to continue to use positive physics as our assessment mode. I'm hoping that when we do the energy work momentum unit, that we can actually do some paper and pencil on in person for many of you tests. I know not everyone will be able to do that, but hopefully most of you will be able to, because I do want you to, if you can, have that experience, be able to do that so that you, I think most of you will probably end up taking a pen and paper in-person test eventually for the actual AP exam. And so I want to give you as much practice at that as we can. But for this time around, still sticking with positive physics. Any questions about that? I can go ahead and shift to the calendar to let you see the due dates, but any questions about the schedule? Looks like it's still trying to load here. There we go. All right, actually, before we look at this, let me just show you the calendar to make sure you see the due dates on here. So I go to assignments, click on calendar view, click on month view. You can see there's actually nothing due this week. Here is today's date, 22nd. A week from today, Unit 10's positive physics assessment. And then the Tuesday after, we don't have school on the 8th, or at least students don't have school on the 8th. We have a teacher in service that day. So on the 9th, we'll be meeting for A Day, and that'll be when the 15th unit is due. And then on the 11th, that's the 16th unit's only, I think, 6 questions or something. It's pretty short. So that's, you don't have as much time for that one, but it's a much shorter. And that 11th is probably the day that we'll be finishing the whole unit on rotational motion. So it's kind of a culminating activity as we wrap things up. All right, so hopefully that makes sense. What we're going to do today is start with going over a couple of questions from worksheets 2 and 3 that we ran out of time for. And then we're going to look at a new worksheet, also in topic 7. But let's go ahead and go to worksheet 2 and 3 first and wrap that up, since we didn't have a chance to finish before the break. If I remember correctly, we did not have a chance to get to this question. Am I remembering accurately for you guys? It was different in every class, but I've made some notes, and this is what I have that we need to still cover this car problem.
Which worksheet is this?
Worksheet 2. You guys agree that I have my notes correct? Hopefully.
Yeah.
All right, good. What was that, Julie?
We hadn't done 2 either, but I don't know if you.
Oh, we didn't do number 2 either?
I don't have that down.
Oh, yeah, that one we didn't solve together in class because it's a lot like number 1. It's just at the top of the hill. I guess we could do a quick talk through. It's kind of the same situation as number 1, where you're doing the motion map. And so if we look at the acceleration vectors, they all point to the center of the circle. And if you look at the velocity vectors, they're all tangent to the circle. So if you remember on number 1, it was at the bottom of the hill, but the map was the same kind of an idea, where the accelerations point to the center and the velocities are tangent. And then it's very similar in part B. Is the car accelerating, and what's the direction? Well, it has to be accelerating because the velocity is changing in its direction. And even if the velocity's magnitude is constant, even if the speed is constant, because the direction is changing, it has an acceleration. And its acceleration would be centripetal in nature because along this curve, it's following a circular pattern. And the acceleration will be directed to the center of that curvature, or to the center of that circle, the kissing circle. So very much like what we did on the other one, number 1. If we look at the math for part C, if this, and this key is also online, so I did put it online for you guys to refer to. So if we go too fast and you need to see some of it again, you can look it up on Axis. But for part C, if the speed of the car is 43 kilometers per hour, its mass is 1,200 kilograms, and the radius of the hill is 25 meters, determine the magnitude of the centripetal force. Remember, the centripetal force for something moving in a circular motion, well, it has to be to have centripetal force, but the centripetal force is the net force. And so if we think about that here, we can see that the weight would be just 1,200 kilograms times the acceleration due to gravity, or about 12,000 newtons. And that's sort of irrelevant for part C. I'm not really sure why they included it there. We do need it for part D, but not really needed right there. Anyway, the next line is what we need. And the tricky part on this one is you can't leave it as 43 kilometers per hour. You do have to convert it to meters per second because newtons are in kilogram meters per second squared. So if you don't convert the kilometers per hour to meters per second, then you're not going to have units that match up. And we need to get newtons as our final unit since it's a force. So that speed has to be in meters per second. So we convert the 43 to 11.9 meters per second. The radius of curvature was given, and the mass of the car is given. And so we'd have a net force of 6,800 newtons to the center of the circle. And then in terms of a force diagram, or anytime on these worksheets they call it a force diagram, what you really need to do is make a free body diagram, because that's what College Board might ask you to draw. They're not going to ask you to draw a generic force diagram. If they do ask you to draw something, it'll be a free body diagram. So for this one, we've got the 12,000 newtons, which they've already shown the work for up in part C, even though it wasn't needed in part C. That's where they showed how to calculate that. That's the downward gravitational force, or weight. And then the net force is 6,800. So if I think about the net force being the weight minus the normal force would be the weight plus the net force. And the net force is downward because it's to the center of the circle. So 12,000 minus 6,800 gives us 5,200 normal force. And if we think about what that would feel like, the actual weight is 12,000 newtons, but it only feels like 5,200 because it's going up and over the curve. And so that makes sense. It should feel lighter. It should have a lighter apparent weight. And remember, the apparent weight is the normal force. The real key is to make sure you remember the difference between net force and normal force. A lot of times students get confused and they interchange those. And there are cases when the normal force could be the net force. There are situations where that can be true, but it's not very common, first of all, and it's very situational. So anytime something's moving in a circle, the net force is the centripetal force. And only in certain circumstances would that be the normal force. So we do have to be careful that you're keeping in mind what those two words mean and how they're different. So any questions on number 2? Just a quick overview there. All right, number 3. And again, if you want to look back at this, if you are trying to write some things down and didn't have time to do it in this short overview, the key is on Axis in the same place where the worksheets are. And so you can look that up as well. For number 3, we're switching gears and talking about roads and cars making curves. And it says at the top, roads are banked or tilted in curves in order to make turning a car at high speed safer. So if you think about a car on an off or on ramp of the highway, those curves are angled. They're not just curved, but they're angled. And there are other curved roads that are angled as well, but they're just letting you know that that banking, that angle of the road, is to help provide some normal force to assist the car in making the curve. But then for part A, it says, while that's true, for a situation when the road is unbanked, draw a force diagram or free body diagram for us for a car coming towards you as it is turning. So if it's turning to its left, if you're in the driver's seat, it would be to the left. If we're looking at the paper, it's to our right. The car is turning And so we would have its weight force down, its normal force up, and because the ground is level, the ground is not banked, those two would have to be equal and opposite, equal in magnitude and opposite in direction. Otherwise, the car would rise or fall. And since it's not rising or falling, those should be equal value and opposite direction. But for the car to make the turn, there has to be some force that allows the car to turn. And in this case, it would have to be friction. There would have to be friction between the tires and the road for the car to be able to navigate the turn. And you can see in the diagram here, they tell us that the acceleration and the net force would be to the center of the turn, because if it is traveling along a curvature, that is a type of circular motion. And if it's circular motion, then the acceleration will be to the center of the curve, and therefore the net force will be to the center of the curve. Can someone, it can be Jilly or Mark in the classroom, or it can be someone that you can just unmute in the Zoom. Why are they labeling this friction as static friction, even though the car is moving?
Because the tires are gripping to the ground.
Exactly, yeah. For the two types of friction, in case it's a little hazy in your memory, it's static friction and kinetic friction. And while the word kinetic means motion, more generically, it means motion, like kinetic energy is energy of motion. Kinetic friction is a specific kind of motion. It doesn't just mean any kind of movement. So for kinetic friction, it specifically means the surfaces are sliding across one another, not rolling, not moving just generically, but specifically sliding. In fact, some books, rather than calling it kinetic friction, call it sliding friction. I think we mentioned that when we were first learning about it. So it's static friction because the wheel is not sliding across the road. If the wheel was sliding across the road, they wouldn't be able to turn. That would be if you were hydroplaning or hit ice or something like that, you'd be skidding. But the wheel's not sliding across the road, it's actually gripping the road. And so for it to grip the road, we would call that static friction. The wheel is not sliding. So any questions about part A? All right, part B. Now, I'm not real crazy about their diagram here. I'll let you look at it, but I have my own that I've drawn at the bottom of the page here that I'll show you. Mine is hand drawn, so it's not quite as fancy as theirs, but I think theirs is missing a key feature, or maybe oversimplifying a key thing. And in fact, one of them I would argue is not really very accurate. So I'll show you mine, but so don't worry too much about their drawings, but I want us to read the scenario, and their word explanation makes sense. So it says, for the situation of a banked road, draw a force diagram for a car moving toward you as it's turning, same direction of turn. Identify all the forces and components of forces that contribute to the force needed to make the turn. Well, in this case, because the road is banked, the road has a little bit of a push, not just up, but also to the side because of its angle. If we think about the normal force having components, which is kind of how they're drawing it in this left diagram, which I think is a little bit better. They're showing that normal force is pushing up, but it's also pushing to the center of the circle. So that normal force is assisting the friction to help the car navigate the turn. The weight force would be down, and it would be congruent to the y component of the normal force. It wouldn't be actually congruent to the normal force itself, since the normal force is angled. Remember, normal force means perpendicular to the surface. So this picture over here on the left, I think this one's fine. This is the one on the right is the one I'm not crazy about. So I've kind of redrawn that. For their explanation, though, it says, if the car is moving at a speed where friction is not needed, the force turning the car is the horizontal component of the normal force from the road on the tires. If going faster or slower, friction is needed, and the horizontal component of the friction force keeps the car from sliding down the bank at slower speeds or provides additional force enabling the car to turn at faster speeds. So I want to talk about all three situations with my diagram that they've mentioned here in this paragraph. And that's where I think their second diagram, if there's a little bit, it's a little bit confusing, because I think you would assume that means if friction is needed, and it's driving at a faster speed, and it's actually the other way around for that picture. That's why I'm not crazy about it. So here is my diagram, and one thing that I've done different is, instead of like they have, making the normal force have components, I've done what we did before when we had angled surfaces, and I've angled my axes to match the surface. Did I need to do that? No. But if I don't do that and there is friction, both the normal force and the friction are going to have components, and I'm going to have to do trig for two different forces. If I do spin the axis just a little bit to match the slope of the road, then the normal force is on the y-axis, and any friction force that I draw is going to be on the x-axis, and only the weight has components. So I'm going to limit how much trig I have to work through. So I think it's wiser to set the problem up with an angled axis like I've drawn. And hopefully you can make it out well enough, but I'm showing the normal force is perpendicular to the surface. And so with my angled axes, it is along the y-axis. And the weight force is always straight to the center of the earth, so straight down. And then I would have to find a y and an x component for that weight force. So the way I've drawn it, I'm showing that the normal force is actually congruent to the y component of the weight force. The x component would be the part of the weight force that's pushing the car down the slope. So if you could imagine the car sitting still on this slope, if there was no friction, if it was just like a super slippery, icy slope and it was just trying to sit still, the car would slide down the ice, right? And so there is a force of gravity, or at least a component of that force of gravity, that would make it want to slide down the slope. And that's that x component of its weight. All right. The one thing I do like about their picture up here on the left, this one, is that it helps you see, if you draw it this way, you can see that the x component of the normal force is pushing the car to the center of the circle. So I do like that. But if we're going to solve a more complicated problem, it gives us a lot more math issues. So I just prefer to angle the axes and address it this way mathematically. Now here's the part that's maybe I don't think they do a very good job of explaining here. It's clearer in the paragraph, but I don't think it's real great in their pictures. So let's talk about the first scenario. The first scenario is this car is traveling at the perfect Goldilocks speed. You know, Goldilocks story. It's not too hot, not too cold, it's just right. So here it's not too fast, not too slow, it's just right. Okay, they're traveling at that perfect Goldilocks speed. So perfect that the angle of the road provides enough inward push that they don't even need friction. If it was a purely icy, almost zero friction road, they're going at that perfect speed where they don't even need the friction. It's fine. That component of the road pushing is going to be enough to make the car turn the turn without any friction. And what I've drawn on my picture, or on my page right now, is exactly what the free body diagram would look like in that Goldilocks scenario. That x component of the weight is sufficient to provide enough normal force pushing it back and allowing it to turn in a turn without any friction force required. Now, if the car, let's say the car was sitting still, not even moving, but just sitting still on this slope, the weight would make the car want to slide down the hill. If there is friction so that it doesn't do that, which direction would the friction be, up the hill or down the hill? If the car's just sitting still.
It would be up the hill.
Uphill.
Yeah, up the hill. The weight of the car would naturally make the car want to slide down. So if it doesn't, friction must be holding it up, right? So if it's just sitting still, or if it's going really, really slow, below the Goldilocks velocity, super slow. So if it is either still, just sitting there, or super slow, then the friction is going to be directed up the hill to keep it from sliding down. That is probably the least likely real life scenario. You know, hopefully you don't find a car sitting on an off ramp. That's not good. It could happen, but it's not normal, right? And hopefully they're not going so slow that they actually need friction to keep them from sliding down the slope. And that's also probably very unlikely. So while it's possible, it's probably not particularly likely. It's possible that they're going at that perfect Goldilocks speed where they don't need friction. And that is often what the question asks about on AP exams. What is the velocity where friction wouldn't be required? And you're basically just finding out the velocity where the centripetal force is that X component of the weight. But the more likely scenario is when we're driving on an off ramp or an on ramp, we're going faster than that Goldilocks speed. And so in that case, the friction force, our car is going fast enough that its inertia would be driving the car up the ramp, right? If we were driving a normal speed on around that curve, if we hit ice, we would slide up the ramp and off, right? We would keep going in a straight line instead of making the curve. So under normal speeds, the most likely scenario, the friction would be down the slope. So if we say like normal or fast speeds, the friction would be down the slope. And if you were trying to figure out the friction force there, the centripetal force in this third scenario would be this downward friction force plus the X component. Both of those things are helping the car turn the corner, the X component of the weight and that friction force. So you'd have to add them together. And together they would be equal to the net force that's causing the centripetal turn. So there's lots of ways they could take this question. The two most common that I've seen are, what is the friction force if it's traveling at a certain speed? So you would use the, remember our centripetal force equation is mv squared over r. So if you know the speed and you know the mass of the car and you know the radius of the curve, you can find the centripetal force. And if it's in this normal or fast mode here, that's going to equal the friction force plus the X component of the gravity. So that's one way that I've seen it where it's moving at a normal or typical or faster speed. I've never yet seen it where it's going slow or stopped, but potentially they could ask it. Any questions about this one?
So actually, never mind. Never mind. I got it.
Okay. So let me change colors here. So this is if it's fast. If it's slow, I'll switch colors here. Then it would be the you'd have to find the difference between the friction force and let's see, the friction force and the weight force. So instead of adding them together, you'd find the difference. That would be if it's slow or stopped. The most common example is if it's that Goldilocks, like the velocity where it doesn't even need friction. That's the most common example I've seen. And in that case, it's just the X component only. Oh, and sorry, I forgot my X here. So there's three scenarios, and you have to kind of figure out what is the force pushing to the center of the circle. And so depending on the speed of the car, it could be any of those three.
Could you please repeat what is FGX again?
It's this X component down here of the weight force.
Oh, okay, okay, okay.
Any other questions? For uniform circular motion, I think this is probably the most complicated question. And it's not extremely common, but there's usually at least one question about banked roads or unbanked roads somewhere on the exam. So I want to spend some time discussing it because you'll probably see at least one question somewhere. It might just be in the multiple choice, but you'll probably see something somewhere about this concept. All right. Like as I mentioned earlier, I'm also recording this. If you need to go back and listen to it again, it'll be posted later too. All right. Let's go ahead and move on to the next question. So we've got a yo-yo pro swinging his yo-yo around the world. Draw the force diagrams for the yo-yo at each of the 4 positions shown: top descending side, bottom ascending side. For each of the positions, indicate which force or combination of forces provides the force needed for circular motion. In other words, show the combination of forces that would help you determine the net force or the centripetal force. So if we think about this scenario, this is like swinging the bucket that we talked about before break. At the bottom of the swing, the string is going to have enough tension to bear the weight of the yo-yo, but it's also going to have to pull against not only that weight, but also pull against the inertia of the yo-yo wanting to continue to travel in a straight line. And so you're going to have that tension force being much larger than just the weight. It has to bear the weight and it has to change the direction of the yo-yo. So the tension would have to be larger. The string would feel tighter and you would feel more pressure against your finger at the bottom. At the top, the weight is down and the tension is down. So you could spin it at a perfect speed where technically at the top of that loop, at the very peak, the tension could be 0, where you're going at just that, again, that Goldilocks speed where it's going perfectly around. And when it gets to that peak, the weight force is the exact amount it needs to be the centripetal force. And you don't even need tension in the string. So again, if you have a yo-yo, if you just take a kettlebell or anything that you can swing in a vertical circle, you can feel at the bottom of the circle, it's pulling on your arm or your finger much more strong. And at the top, it's much more relaxed. And if you adjust the velocity, especially like if you take a bucket of water or a kettlebell or something and you swing it in a vertical circle, you can adjust the velocity where at the top, your arm feels totally relaxed. There's no tension in your arm, okay? It has to be at just that right speed, but it's possible to do that. Now, on the 2 sides, the weight isn't fighting against the tension in the string or helping the tension. They're perpendicular. So the weight of the yo-yo is sort of unimportant in terms of the centripetal force on the 2 sides. And it's purely the tension in the string that's providing the centripetal force because the weight is perpendicular to it. It has no impact at those 2 perfect 3 o'clock, 9 o'clock positions. No worries, Lily. Any questions about this particular example? All right, so thinking through this yo-yo kind of an example, you would want to make sure that you understand where the tension force is. I'm going to be putting you into breakout groups here in a little bit, and you're going to be thinking about a roller coaster. But when a roller coaster goes in a vertical loop, it's this same scenario, and you're going to be working through some problems like that today. All right, well, let's move on. Let's look at another example here. Let's go to worksheet 3 now. So worksheet 3. Looks like I'm gonna have to change my share. I thought maybe it would let me get away with it since it was the same program, but apparently it doesn't work that way. There we go. So worksheet 3, we're just gonna look at problem 1 together. This would also be like a roller coaster kind of a question. It says a woman flying aerobatics executes a maneuver as illustrated below. Construct a quantitative force diagram, meaning put numbers on it, not just letters, of all the relevant forces acting on the woman flying the airplane when upside down at the top of the loop. So on our free body diagram, the dot is not the plane, the dot is just the pilot, just the woman. All right. So the dot represents the woman. Well, the woman being made of matter has mass, and having mass means gravity is going to be pulling on the mass, creating weight. So the woman's weight would be the mass of the woman multiplied by the acceleration due to gravity. And you can see on the picture, it says that this woman's mass is 55 kilograms. So the woman's weight would be 550 if we just use 10 for the acceleration due to gravity. It also shows you on the picture there that the radius of curvature here for this circular aerobatic loop is 380 meters. And it also shows you that the plane is moving tangent to that circle at 235 kilometers per hour. So if we look at the free body diagram, when she is at the top of that loop, she's below the seat, right? The seat is above her. And so the seat would be pushing against her, but pushing her back to the center of the circle. So the normal force of the seat is not lifting her anymore. The normal force of the seat is actually pushing her back to the center to help keep her moving in a circle. Her natural tendency as she rises up along the side of that loop, her body would want to keep going tangent to the circle. The seat has to push her back a little bit to keep making her stay in the circular path. But the seat wouldn't have to push that hard because her own weight is also assisting in that pulling her back to the middle because it's also directed downward. And at the very peak, it's directed downward right through the center of that circle. So the normal force and the weight force are exactly in the same direction, just different magnitudes. Now, to find that 70 newtons, though, that's not given. We have to actually go through some steps to figure it out. So here's a couple steps over here. The first thing they've done is they've taken the weight of the pilot times acceleration due to gravity and found her, or sorry, the mass times acceleration due to gravity and found her weight is 550 newtons. Then they've determined that the net force, because the plane and the woman are moving in a circular pattern, would be centripetal. And centripetal force is mass times acceleration, but very specifically, the centripetal acceleration. And we know centripetal acceleration is v squared over r. So the net force or the centripetal force would be mv squared over r. We know the mass of the pilot, 55 kilograms. We do need to convert the speed of the plane from kilometers per hour to meters per second. Just like the previous problem we looked at in worksheet 2, if they give it to you in kilometers per hour, you need to convert it to meters per second because newtons is kilograms meters per second squared. So our units have to match. So we change the 235 into meters per second, multiplying by 1,000 meters per kilometer and dividing by 3,600 seconds per hour. And then the denominator is just the radius of the circle, which in this case is 380 meters. So we can see that the net force, the centripetal force, is 617 or about 620. Now you don't put the centripetal force on the free body diagram, just like you don't put the net force on the free body diagram as the net force. There are certain circumstances where the net force will be equivalent to a particular force, but that's not the case here. The net force here would be the sum of these two forces. So the net force would be the weight plus the normal force, since they're both pointing in the same direction. And the net force is the 620 that we just found using the concept of circular motion. The weight force is 550, which we found earlier, and the normal force is what we're trying to find. So if we subtract the 550 from the 620 to isolate the Fn, we can see the normal force of the seat pushing on the pilot is only 70 newtons. So she would feel just a light push by the seat to keep her in the circle. Questions about this example? If you did work through some of these worksheets on your own over the break, then you may have already worked through this one. But if you did not, I wanted to make sure we had at least a chance to talk about it briefly. All right. So what we're going to do next is actually give you a chance to practice some problems, but not from these worksheets. I did put keys for all of those worksheets on Axis, worksheet 2 and 3 and 4. We haven't even done any questions from worksheet 4 together, but you should have the worksheet either in print form or available on Axis, and the keys are all there. But we need to look at, or I'd like you to look at the review sheet. So let's go back to Axis and let me help you make sure you can find it. So on Axis, and for those of you in the classroom, for Mark and Julie, because I'm isolated at home and can't come to campus, I wasn't able to print them. So this review sheet we're going to look at isn't available in the classroom. So you'll just have to look at it online as well. But it'll go to topics. So you're going to go to Axis. And so so Mark and Julie, you'll have to get online as well to look at this. So go to topics. And we're still in unit 7 on our units. I combine circular and rotational together. They are different, but they're similar enough that I combine them together. For College Board, it's unit 3 and unit 7. So they're very separate in their flow, but I prefer a different flow of content. So you're going to go to unit 7, just where we had been before. Over here on the right, you can see there's notes, the intro worksheet we did, worksheet 1, 2, 3, and 4, which we've talked about, solutions for worksheets 2, 3, and 4. And then the review worksheet right below that is the one I've just recently posted this weekend, and the one that I want to focus on today. So I put both versions today, since I wasn't able to print them for those of you that are on campus. I decided to put both the document form and the PDF form in case you want to print it. If you'd rather just look at it on the screen, that's fine. This won't be an assignment that you turn in. This will just be something we're going to work on together in class. So however you're going to open it, go ahead and get that open. This motion review worksheet. Once you have it open, this is what it looks like. So just to make sure we're all in the same spot. All right, I'm going to talk through part 1 with you, and then we'll put you into breakout groups and have you try the rest of it. So not the whole worksheet, but the rest of this scenario. That's fine. Yeah, if you need to get it from your printer, go for it. If you want to look at it on the screen, that's fine too. So in this question, and I've actually seen questions similar to this in FRQ form on the AP exam at different times. Not recently, but at least not exactly like this, but I have seen them before, and I've definitely seen multiple years where there's questions like this in the multiple choice. So what we're looking at here is we got this roller coaster track, and we're looking at the same cart in a variety of different places. Or it could even be a different card. It doesn't matter, but we're looking at it at several different instances. Because remember, whenever we look at a free body diagram, we're looking at one point in time. So for picture A, we're looking at that point in time where the cart is right at the top. And that's what number 1 asks about. At the top of the first hill of the roller coaster, point A, A 60-kilogram passenger feels as if she weighs 500 newtons. Explain which force provides the sensation of weight. How fast is the roller coaster going over the 3-meter radius hilltop to create this sensation? And then draw a quantitative force diagram for the situation. So let's start with just figuring out the free body diagram here. If we know that the weight of this person, this passenger, would be downward, how do I find, it says it wants it to be quantitative, so how do I find the value for that weight?
Mass times gravity.
Good. Mass of 60 kilograms times gravity. What's it give us?
600.
600.
Good. Now, in the middle of the question, it says, explain which force provides the sensation of weight. So it's kind of worded funny. I think what they're trying to ask is, when we talk about how your weight feels different at different points, that's really your apparent weight. What's the actual force that we often refer to as apparent weight? What's the more scientific name for that force?
Normal force.
Normal force. Good. So what's her normal force?
500.
Good. And because they're at the top of the hill, the seat is beneath her or him. I guess it doesn't. Oh yeah, it says she. So the seat is beneath her. And so the normal force is pushing up against her. And her weight is down. But she would naturally feel lighter in her seat at this point because it's going up over the crest of the hill. So her inertia is wanting her body to go in a straight line tangent to the hill, but her weight enables her to not just keep going straight because of the gravitational force. So she feels lighter in the seat. So we've answered that first question, explain which force. That's the normal force. We've made our free body diagram, so we've done this part. Now we just need to figure out how fast is the roller coaster going over this 3-meter radius hilltop. So when they say the 3-meter radius, what they're saying is we could draw our kissing circle, not a very good circle here, but hopefully you get the idea. We draw our kissing circle, there's the center, which means the net force is down to the center of the circle. And that also means the acceleration is down to the center of the circle. All right, so does anybody have any suggestions on how to get started? Maybe not how to solve the whole problem, but what could we do to get started here?
Would we have to like the force of like it's like mass times velocity squared over the radius, so like we should start with that equation, I guess.
Okay. What would that's a good place to begin, or at least to get to at some point. Mv squared over r. What is mv squared over r equivalent to? What force is that?
The centripetal force.
The centripetal force. All right. So the centripetal force is mv squared over r. Now, what do we know? What else do we know about centripetal force for objects moving in a circle?
That is also a net force.
Yeah. So that is also the net force. Well, can we figure out the net force from what we know already?
Yes.
What is it?
100 newtons.
100 newtons, yeah. So we know the net force is 100 newtons. And we know that that is also the centripetal force, which would be mv squared over r. Well, do we know the mass?
Yes.
Yeah. Do we know the radius? So if we say 100 newtons is equal to mass, 60 kilograms, times v squared over a radius of 3 meters. We actually know everything except for the velocity, right? And that's what the question wants us to figure out. How fast does it have to be going for this sensation to be accurate? So when you figure out what V is, go ahead and solve it. If you're in the classroom and don't have a calculator, I have some on the back table there you can borrow. But go ahead and calculate V. And when you get an answer, type it in the chat. And then for Mark and Jilly, I'll just ask you in the class what you're coming up with. Getting a pretty consistent set of answers in the chat. Jilly, have you finished getting an answer for V yet?
Yeah,
What'd you get?
that was about 2 meters per second.
Yeah. So if we look at these numbers, the 60 only has 1 sig fig, the 500 only has 1 sig fig. So if we do want to round it, which this curriculum frequently gives numbers with only 1 sig fig, which is kind of annoying, but if we wanted to follow that just for practice, it would be 2 meters per second. I think it's about 2.2 something, like most of you are coming up with here in the chat if you don't round it. So that's how we would solve question number 1.
Mr. Loeb, I have a question.
Yeah.
How would you depict that a number has 2 sig figs if it ends up being like 300 or something like that?
So if you had a 300, you have 2 options. You could do 3.0 times 10 to the second so that you show it that way. Or you can just put a line over the 0 that is significant. Any other questions?
For this is asking for velocity. What about like the other equation, v equals 2 pi r over t? Well, we don't have the value for t, but if we do, can we use it?
Yeah, for objects that are moving in a curve rather than a true circle, you're not normally going to be given the value for t, because t is the amount of time it takes to make a full circle. And for objects moving on a curve, they actually never do make the full circle. They only go over part of it. So you wouldn't normally have that information for this kind of a problem.
Oh, okay. Yeah, that makes
For the previous problem, like with the yo-yo going in a circle, where it keeps going around and around, that would be a different kind of problem where you might be given that information.
okay.
Anything else you want to ask? All right, well, I'm going to put you guys into breakout rooms and have you solve some of these problems. Let's see how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's have you in 4 groups. And I just got to make sure that Gavin is stuck with me in the sub, so we don't want that to be the case. I think Mr. On could probably help you, but we'll leave it to you guys. All right, let's see here. Make sure everybody's got someone in their group. Okay, that's good. So group 1 is going to be Haley, Jenny, and Lily. You guys are responsible for solving number 2 and teaching that to the class. And so each of you should give some contribution to the teaching part, and you need to show it somehow on the screen so that we can see it. Rather than just holding the paper up to the camera, it's really hard to see that way, especially on the video. Group 2 is Carson and Gavin. You guys have question 3. All right. Group 3 is Carter, Frank, and Jackson. You guys have question 4. All right. Group 4 is Atticus, Dasha, and Roy. You guys have question 5. Actually, let's have you guys do question 6. Okay. So Atticus, Dasha, and Roy, you guys do question 6. And then since there's only 2 in the room, it's slightly easier. So you won't have as many people to help talk it through. So for Jilly and Mark, you guys have number 5. All right, everybody understand what to do? All right, go ahead and I'll put you in your groups and get to work. For Jilly and Mark in the class, you may want to have one of you go ahead and log in to the Zoom so that you'll be able to show your work. Without me being there with my laptop, it's going to be hard for the OWL camera to pick it up with enough detail.
Do you care who joins?
No, either one of you is fine. I mean,
All right.
you both can, or just one of you can, doesn't matter.
All right, Haley, you're sharing the screen. Okay.
And you may want to just give a quick overview, because not everybody's read your questions. So just a quick, what's the scenario for your question number 2?
Yeah, so our question is, oh, do you want to explain it, Haley, or? I got it.
I was gonna read the question so that way we all had like a part and then you guys can explain. So our question was, at point B, the roller coaster has reached a speed of 28 meters per second. How large must the radius of the valley be so that a 100-kilogram rider will experience a normal force of 5 times their weight? And draw a quantitative force diagram for the situation. So we did that.
Haley drew the force diagram, so you see it. So because the rider has 100 kilograms of mass, their weight will be their mass times the weight, which would be 1,000 newtons. And if the normal force has to be 5 times the weight, it's going to be 5,000 newtons. And so the net force will be the 5,000 minus the 100 because it's at a valley, so it's not going to be additive, it's going to be a difference. And then Jenny will go into the math of it.
Yeah, so since the net force is 4,000, you'd use like the centripetal force equation, which is m times v squared over r. And if you do the math, which is 100 kilogram times 28 meters per second squared, divide that by 4,000 newtons, and you would get 19.6. And using sig figs, which would be 20 meters.
All right. You can leave that on the screen just for a few more seconds in case anybody has questions. All right, one of the other groups has a question about G's, and I don't think we're going to get to their group today, so just I'll make a comment now. So it says 5 G's. That means the weight that you feel, the apparent weight, is 5 times greater than your actual. So the way you find your G's is to take apparent weight divided by actual. So in this case, 5,000 divided by 1,000. So 5 would be the, when they say 5 G's, that's what that means. All right, let's have one more group go. Let's see if we can get through number 3.
Yeah, I'm gonna share.
Yeah.
Quickly. Oh yeah.
So this question is for point C, and it says there's a 70 kilogram rider, and he's traveling at 20 meters per second with a 7 meter radius, and it's just asking to draw a quantitative force diagram. We can figure out the weight force because his weight 70 kilograms multiplied by 10 meters per second squared. That's 700 newtons for the weight force. And then the centripetal force, they give us everything we need for mv squared over r, and that'll get you 4,000 newtons for the centripetal force.
Yeah, and that normal slash centrifugal, because they're both kind of are just the same thing. They are also the net force. So the net force is 4,000 newtons. And then just off to the side, it wasn't a part of the question, but those are the velocity and acceleration vectors at point C.
Good, I like it. Velocity is tangent to the circle, perpendicular to the acceleration, which is to the center. I like that. In terms of labeling the free body diagram, net force is always the sum of the forces. And in this case, because it's moving in a circle, it's also the centripetal force, like they said. And I would encourage you, it's fine the way you labeled it, because you're showing that the normal force is the centripetal force here. But in general, you wouldn't want to label it just centripetal force, which they didn't. I'm just speaking more broadly for future reference. You wouldn't want to label it just centripetal. That's too generic. And you wouldn't want to label it net force, even though in this case, in terms of its circular motion, it is. Horizontally speaking, it is the net force. You would want to label it, what kind of force is it? Friction, tension, in this case, normal force. So remember, centripetal force is a generic force causing something to go in a circular pattern. In this case, at this position, it is purely the normal force of the track pushing the car back. So kind of like the yo-yo problem, since it's right on the side of the loop, the push of the track is kind of like the pull of the string in the yo-yo. All right, so we are basically out of time. Any questions about that one though before we dismiss number 3? All right, I'll make a note that we need to finish up 4, 5, and 6. So we'll just do that right at the very beginning of class on Thursday. You don't need to finish the rest of the worksheet or anything. The worksheet is not assigned. The worksheet is just a chance for us to practice and review and keep going through different problems. I cannot put the key for this one online because it's a review sheet, so they don't want us to put those things online. So I can't post it, but I will on Thursday. I would like to go through questions 4, 5, and 6, have the groups explain them. And then I would like to take a look at number 8. So if you want to glance over number 8 between now and then, you can, but your primary assignment would be to start working on those positive physics quizzes that will be due over the next few weeks. So if you have questions for me, you can stick around. If not, you're dismissed. Good to see you guys and look forward to seeing you again on Thursday.
Thank you.
Thank you, Mr. Webb.
Thank you.
Thank you.
Thank you, Mr. Webb.
You're welcome.
All right, guys. Have a good day.
Thank you, Mr. Webb.
You're welcome.